Hello everybody. Today we're looking at a really interesting problem, the arithmetic mean and geometric mean. So the goal of today is we want to show a geometric mean of positive number is always less or equal to the arithmetic mean, which as the following. We let x1 to xn be some positive integer and define the arithmetic mean as the following: x1 plus xn divided by n, and geometric mean divided by the following is the product of x1 to xn, and taking the m loops of that. And we want to show that a is always greater than or equal than g. And this inequality was actually due to Cauchy. So let's get started. So before we go straight to the theorem, we would need one more theorem to help us. Is the following: if we let x1 to xn be some positive number, and the product of x1 to xn, so that means the product of that, so that is x1 to xn, the product of equal to 1, and then the sum of xi is greater than m, that means x1 plus all the way to xn. Okay, so, and it's interesting that this theorem is being used in many different areas. For example, the engineering and mathematics, but somehow they always assume we know this theorem. So we're actually going to prove that today. So let's begin. Proof. So in here we prove by induction. Proof by induction. So the base case is m equal to 2. Then we have that by assumption we have x1 times x2 equal to 1, and x1 x2 greater than 0. By assumption, suppose we have that, then we split into two cases. So case 1, if x1 equal to x2, then we have only one choice, that is x1 equal to x2 equal to 1. Then clearly x1 plus x2 is equal to 2. And case 2, x1 is not equal to x2. That means one of this x1 must be some number less than 1, and the other must be some number greater than 1 in order to get the product of 1, and they are positive. So without lost generality, suppose without loss of generality, assume x1 is some number between 1 and 0, and x2 is some number greater than 1. Then we have 1 minus x1 times x2 minus 1 is some number greater than 0, because that is greater, because this one is greater than 0, and x2 minus 1 is also greater than 0. And if we expand that, that gives us 1, actually, no, is x2 plus x1 minus 1 minus x1 x2, and by assumption x1 times x2 is just equal to 1, so that just equal to 1. Therefore we have the following, and remove the 2 on the other side, we got x1 plus x2 is greater than 2. So that is the base case. Now by the inductive step, assume that the product of x1 to xk is equal to 1. Then x1 passed all the way to xk is greater or equal than k for all x1 xk greater than 0. Now we want to show it. Now what we want to show is by induction is if x1 times all the way to xk plus 1 equal to 1, then x1 plus xk plus 1 is greater or equal than k plus 1. Okay, so once again we separate into two cases. So case 1, okay, hang on. Case 1, if xi equal to xi plus 1 for all I between k and 1, that means x1 equal to x2, x2 equals 3, x3 all the way to xk plus 1. And since their product is 1, that force that xi, that force that x1 equal to x2, xk plus 1 equal to 1. Then we have that the sum of x1 plus x2 plus all the way to xk plus 1 is equal to k plus 1. Okay, now case 2. Now we suppose not all xi's are the same, so there should be at least two xi, like xi and xj, their difference, and then there are at least one xj is between 0 and 1, and xi is greater than 1. So just once again, without loss of generalities, we assume that x1 is between 0 and 1, assume x1 is between 0 and 1, and xk plus should be xk plus 1 greater than 1. Then x1, the product to xk plus 1, we can, that is equal to 1 by assumption, and we can rewrite it as x1 times xk plus 1 to x2 to all the way to xk. And we let y equal to x1 times xk plus 1, then we have that y times x2 times all the way to xk equal to 1. And this is all positive. Then by the assumption we have that y plus x2 plus all the way to xk is greater or equal than k. Then we can, but don't forget what we actually want is x1 plus all the way to xk plus 1 is greater than equal than k plus 1. So keeping that goal in mind, so we do a little bit algebra. So we put x1 plus all the way to xk plus xk plus 1 plus y greater than equal than x1 plus xk plus 1 plus k, and we move y to the other side, we got x1 to all the way to xk plus 1 greater than equal than k plus x1 plus xk plus 1 minus x1 times xk plus 1, and we also want k plus 1, so k plus 1 plus x1 plus xk plus 1 minus x1 xk plus 1 minus 1. And this equality is x1 1 minus x1 times xk plus 1 minus 1 as what we're showing in the base case, and we know that is greater than 0. So we have that x1 plus all the way to xk greater than equal than k plus 1 plus some positive number plus some positive term. Therefore, we have that x1 plus xm is greater than equal than m when their product is equal to 1 and they're all positive. Actually, I'll do that. When x1 to xn greater than equal than 0, and product is equal to 1. Okay, we stop here and we probably prove the main theorem that geometric mean is always less than arithmetical mean in the next video. So please stay tuned for the next video. Thank you.